Hello everyone, I'm Project, physicist from Rwanda Polytechnic. Today's lecture is kinematics of circular motion. After this lecture, you should be able to write and apply relationships between linear variables and angular variables. You should be able to define and apply concepts of frequency and period and relate them to linear speed and angular speed. You should be able to apply the kinematics equations to solve problems of circular motion. Circular motion is defined as any motion whose path or trajectory is a circle. For the object that is moving in a circle is described by two types of variables: linear variables and angular variables. Linear variables are physical quantities which describe the object moving around the circumference of a circle. Examples of linear variables: we have linear position. Linear position is the location of the object around the circumference relative to the reference point. We have linear displacement. Linear displacement is arc length moved by the object from one position to another position. We have linear velocity. Linear velocity is the rate of change of linear displacement, and it is always tangent to the circular path. We have the average linear velocity, which is equal to the displacement divided by the time interval. And we have the instantaneous linear velocity, which is the derivative of displacement with respect to time. We have linear acceleration. Linear acceleration is the rate of change of linear velocity. We have two types of linear acceleration: tangential acceleration and centripetal acceleration. Tangential acceleration, noted as AT, has two forms: the average tangential acceleration, which is equal to the change of linear velocity divided by the time interval, and instantaneous tangential acceleration, which is the derivative of linear velocity with respect to time. Tangential acceleration is responsible for the change in magnitude of the linear velocity, whereas centripetal acceleration is responsible for the change in the direction of linear velocity. Centripetal acceleration is toward the center due to the centripetal force that is attracting the body toward the center of the circle. By definition, centripetal acceleration is the change of linear velocity over time t. And the linear velocity is the displacement over time t. From the figure here, we have two similar triangles. From the first triangle, we have the change of velocity is equal to final velocity minus v0. Change of velocity divided by final velocity is similar to the linear position s divided by the radius r from this second triangle. From this relationship, the change of linear velocity is equivalent to the final linear velocity times the linear displacement s divided by the radius r. Then, from the definition of centripetal acceleration, which is the change of linear velocity over time. We have centripetal acceleration will be the linear velocity v times the linear displacement s divided by radius r times the time t, or the linear displacement divided by time is the linear velocity v. So the centripetal acceleration will be the linear velocity v times linear velocity divided by radius. And finally, the centripetal acceleration is equivalent to the linear velocity squared divided by radius. We have also the angular variables. Angular variables are physical quantities which describe the radius connected with objects in rotational motion. We have angular position as example of angular variables. Angular position theta in radian is the orientation of a body with respect to a specified reference. It can also be defined as the location of radius with respect to a specified reference. The angular displacement change of theta is the angle between the two angular positions, or the angle swept by radius of the circle that point to a rotating body. We have angular velocity is the rate of change of angular displacement of a rotating body. We have two forms of angular velocity. Average angular velocity, which is equal to the angular displacement divided by the time interval. And we have instantaneous angular velocity equivalent to the limit when the variation of time tends to be 0 of the average angular velocity. And that is the derivative of angular displacement theta with respect to time t. We have angular acceleration. Angular acceleration is the rate of change of angular velocity. The angular acceleration can be average or instantaneous. Average angular acceleration is the change of angular velocity over the time interval. And the instantaneous angular acceleration is the limit when the variation of time tends to be 0 of the average angular acceleration. That is equivalent to the derivative of angular velocity with respect to time. The relationship between linear variables and angular variables. The first relationship is the relationship between linear position s and the angular position theta. From this figure, we are going to find that relationship between s and theta. From trigonometry, sine of the angle theta is equal to the opposite side of the angle theta, s, divided by hypotenuse radius. So assume that theta is very small, then the sine of this angle theta is approximately equal to the angle theta. And finally, from the first definition of the sine of theta, we have theta is equal to the linear displacement s divided by radius. And finally, we have the relationship between s and theta. S, linear displacement s, is equal to the radius times the angular displacement theta. So that means that s, linear displacement, is directly proportional to the angular displacement theta. the coefficient of proportionality is the radius r. It means if the linear displacement s increase, the angular displacement theta also will increase. If the object shift from B to another point, the curve will increase, curve S will increase, but also the angle theta will increase. And if the linear position decrease, the angular position also will decrease. The second relationship is the relationship between linear speed and angular speed. So by definition, linear speed is equal to the derivative of linear position with respect to time. Or from the previous relationship, the linear position s is equal to the radius times theta. So as r is a constant, we have linear velocity v is equivalent to the radius times the derivative of angular displacement theta with respect to time. So remember, derivative of theta with respect to time, it is angular velocity. Finally, we have linear velocity is equal to the radius times angular velocity. So it means that the linear velocity is directly proportional to the angular velocity, and the coefficient of proportionality is the radius r. If the linear velocity increase, the angular velocity will increase at the same rate. And if linear velocity decrease, the angular velocity also will decrease at the same rate. The third relationship is the relationship between linear acceleration, tangential acceleration, and angular acceleration. By definition, tangential acceleration is the derivative of linear velocity with respect to time. So from the previous relationship, linear velocity v is equal to radius times omega. As r is equal to constant, so we have tangential acceleration is equal to the radius times derivative of angular velocity with respect to time. Remember, the derivative of omega with respect to time is the angular acceleration. So finally, we have the relationship between tangential acceleration and angular acceleration. The tangential acceleration is directly proportional to the angular acceleration, where the coefficient of proportionality is radius. So it means that when the tangential acceleration increases, also the angular acceleration will increase. If the tangential acceleration decreases, the angular acceleration also will decrease with the same rate. So as conclusion, the angular variables is related to its corresponding linear variable by factor r, the radius of rotation. Period and frequency. Period is the time taken for one complete cycle, or time taken for one complete turn. Whereas the frequency is the number of turns or the number of revolutions per unit time. The relationship between period and frequency. So from definition of frequency, frequency is equal to the number of turns over time taken. For one turn, for n equal to 1, the time will be equal to period, because period is the time taken for one turn. Then the frequency will be equal to inverse of period. Frequency is equal to 1 over period. The period is measured in seconds, and the frequency will be measured in hertz. 1 hertz is equivalent to inverse of second, because frequency is equal to 1 over period, which is in second. Relationship between period, frequency, linear velocity, and angular velocity. As definition, linear velocity is equal to the distance divided by time. For 1 turn, means n equal to 1, the linear distance moved by the object is equal to the circumference. And circumference is equal to the product of 2 pi with radius, or diameter times pi. And the time for 1 turn is period. So replacing this into the formula of linear speed, we have linear speed is equal to 2 pi radius over period. That is the relationship of linear velocity and the period. It means that if the linear velocity increase, the period will decrease. So it is clear, as the object moves fast, it will use a short time. And if the object is moving slowly, it will move for long period. So since the frequency is equal to inverse of period, so we have the second relationship of linear velocity and frequency. Linear velocity is equal to 2 pi radius times the frequency. So this means that when the linear velocity is high, the frequency will also be high. Remember, the frequency is the number of turns per unit time. So as the object moves fast, the number of turns per unit of time will increase. And as the object moves slow, the number of turns per unit time will decrease. Since the linear velocity is equal to the radius times angular velocity, we have these 3 relationships. The radius times omega is equivalent to 2 pi radius times the frequency, equivalent to 2 pi radius over period. So when we cancel radius, we will have the relationship of omega, angular velocity, with the frequency. So you see that the angular velocity is directly proportional to the frequency. When the angular velocity increases, the frequency also will increase. And when the angular velocity decreases, the frequency also will decrease. That's why the angular velocity is also called the angular frequency, because angular velocity is directly proportional to the frequency. And we have another relationship. The angular velocity is inversely proportional to the period. When the angular velocity increases, the period will decrease. And when the angular velocity decreases, the period will increase. So that is understandable, because angular velocity is proportional to the linear velocity. So circular motion. We have 2 types of circular motion: uniform circular motion and uniformly varied circular motion. For uniform circular motion, the velocity is constant. It means that the initial angular velocity is equal to the final angular velocity and equal to the average angular velocity. Consequently, the angular acceleration will be 0, because by definition, angular acceleration is the change of velocity over time. So as the velocity is constant, the change of velocity will be 0. And the angular position theta is equal to the average angular velocity times time. And also remember that the average angular velocity is equal to the final angular velocity and is equal to the initial angular velocity. So from this, formula for position, you can put any angular velocity, being initial, final, or average. And the average angular velocity is the sum of initial angular velocity to the final angular velocity divided by 2. For uniformly varied circular motion, the acceleration, angular acceleration, is no longer 0. It is equal to the final angular velocity minus initial angular velocity divided by t. And as the uniformly varied circular motion, the velocity is not constant, so the difference will be different to 0. Here we have two cases. The case 1, it is when the final angular velocity is greater than the initial angular velocity. So the difference will be positive, the positive angular acceleration. And here we have the accelerated circular motion. For the second case, it is when the final angular velocity is less than the initial angular velocity. For this case, the angular acceleration will be negative, and we have decelerated circular motion. The final angular velocity will be obtained from this definition of angular acceleration. Final angular acceleration is the product of angular acceleration times time plus initial angular velocity. And the angular position theta is equivalent to the average angular velocity times t. From this formula, we have two formula. Remember, from the linear motion, we have demonstrated this. We have the one formula of the angular position theta is a half of angular acceleration times t squared plus initial angular velocity times t. And we have also the angular position is equal to the final angular velocity squared minus initial angular velocity squared divided by 2 angular acceleration. So for solving the problems of circular motion, we're going to use the 3 equations of motion. The first one is for the angular velocity, the second one, and the third. Thank you for watching, and remember to subscribe, like, and share. See you next time.